All right, howdy everybody. Welcome back to Top Comics Pressing. In this video, what we're going to do is have a little bit more science time, especially as it focuses on kinetics. And kinetics, from the standpoint of chemistry, is the study of understanding how fast chemical reactions occur. And it's a very broad field that encompasses both physical chemistry, physical organic chemistry, biochemistry, enzymology, you name it. It's a pretty core concept. And the reason for that is we need to know how fast stuff is happening. And the crazy thing about kinetics is we have some reactions that are so fast they're almost impossible to study because they happen faster than we can detect them with most methods. And then we have some reactions that are so slow they're hard to understand because they're almost too slow to watch. It's like a slow motion video where you only see the same cell every single second and it never gets to that second cell. So that's very annoying. And because of that, then we're going to have a wide range of methods that are used to study kinetics in a chemical lab. But what I want to do is actually just walk you through some of the basic theory of kinetics. And to do that, let's just start with kind of a assumed basic reaction. And so let's just assume we're taking hydrogen peroxide and we're going to react it with our comic book. And we're going to try to generate a new looking comic book with some kind of stain removal and whitening chemistry. And so in this case, we might say that the overall rate of that chemical reaction is going to be proportional to a rate constant. That's little k. So if you remember when we were dealing with KEQ or Ka from the acids and base video, that was the capital letter K. And so that is the equilibrium constant. This is the rate constant, which is lowercase k. Now, why we use k for constant when constant is spelled with the C, I don't know. I don't make these rules up. Don't blame me for it. That's just what's done. But anyway, so capital K is an equilibrium. Lower k is a rate. If you want to understand the difference between an equilibrium and a rate in the most straightforward way, the equilibrium tells you where you're going to get to at the end when everything is calmed down. And the rate is going to tell you how fast you're going to get to the equilibrium or to the end value. So you can get to that end value very fast or very slow. And in chemistry, we have both reactions that are so fast, they're difficult to measure, and some that are so slow that they're hard to even observe because they barely happen at all. Now, that rate is going to be proportional or equal to that rate constant, and then it's going to be directly related to the concentrations. And so these square brackets here with whatever we have inside them, that's the concentration. And the concentration is going to be very important. Okay, and the easiest way to understand that is kind of the classic saying that the dose makes the poison. And, you know, you probably have a pretty good understanding of that just qualitatively. So if you take one Tylenol or one aspirin to help you out with a headache, that's a good thing. If you take the whole bottle of Tylenol or aspirin, you might end up in the hospital or worse, and that's a very bad thing. So we don't want to do that. If you want to put it in a little bit lighter tone, you know, on a good Friday night, I might expose myself to a low dose of ethanol here by enjoying a Spotted Cow Grand Cru from New Glarus Brewing. By the way, New Glarus is one of my favorite breweries on the whole planet. So if you ever get the chance to go to Wisconsin, I strongly encourage you to enjoy not one, but maybe two New Glarus beers. So this might be a low concentration. That might lead to an enjoyable outcome. We will say that this is, you know, controlling the amount of peroxide in your comic book to get a good result. But let's just say you go overboard. You know, you might end up like this guy, having far too much exposure and really overdoing it. And so he's for sure going to have a bad day after that occurs. So the concentration here is going to end up being very, very super important. And the reason for that is that the rate that we observe is going to be directly proportional to that concentration. And most of the time, people in kinetics like graphs, and we like graphs because the math is just really complicated. It requires matrix algebra and I don't know. I get lost in the math just as much as I think most people do. So, but I like graphs, and for most reactions, and this one we might call a second order reaction. And we get there because it has not one chemical, but two chemicals bumping into each other. So we're going to take that hydrogen peroxide, we're going to take that comic book, and we're going to require them to do something together to make our new comic book. And so that requires the peroxide as one chemical, and the comic book is a second chemical. And by putting them together, we're going to require a second order reaction to get there. So what we're going to look at here then is the effective time as a function of the hydrogen peroxide in this reaction. And it turns out, you know, it drops off very quickly. And the reason for that is whatever peroxide we load on there starts to react. And that's why we put it on there in the first place, is to get it to do some kind of productive chemistry. But as it consumes that hydrogen peroxide, the amount of hydrogen peroxide that's left, so if this is what we started with, and this is 0, you know, as it proceeds, we're going to consume it and it's going to eventually drop off. Now, it won't ever actually get to true 0, but it'll get effectively to 0 at some rate. And because of this, you know, as you proceed in a reaction here, the first little bit, let's just say while it's active under a hop and bleed procedure, we're going to consume a lot of hydrogen peroxide in that window, and we're going to have a very large change here on the y-axis, the height of this reaction, over a very short period of time. But if we go out to this long range here, you know, at the very end, you can have a very long time with almost no detectable change. And that's because you've used it all. It's already done most of its thing, and there's very little of it left. And so this is the basic reason why I think when you're worried about, you know, are these comic books going to decompose into dust because they were exposed to hydrogen peroxide? I really doubt that. And the reason I doubt that is because most of the hydrogen peroxide has been consumed. It has already decomposed off the comic book. And the background rate of that hydrogen peroxide doing something else also, you know, just goes away with time. And it's just a function of having, you know, this kinetic plot that is dependent on the concentration that's left. Now, importantly, the concentration when we're dealing with peroxide is just not the same percentage that you might get. So people ask me, how much hydrogen peroxide do I use on my chemistry? And I usually take 3%, cut in half with water, and that gets me to 1.5% hydrogen peroxide. So that's my standard amount, but that is not really the concentration. That is the concentration of hydrogen peroxide in the bottle I'm using. So if I take my squirt bottle and I spritz on, you know, 1 spritz of hydrogen peroxide, or 2 spritzes, and I spritz on, you know, 2 with 3%, or I can spritz on 4 with 1.5%, those are going to deliver the same amount of hydrogen peroxide to the paper. You know, whether it be 2 spritzes of 3 or 4 spritzes of 4, or sorry, 4 spritzes of 1.5%, you're going to get the same amount. And so importantly, it's not just starting with a reasonable concentration, it's also making sure that, you know, you're controlling how much you add to either an overlay or a mist procedure or in a hop. And so being mindful both of the concentration and of you know, how much you're adding is going to be very important. The other thing I'll point out is if we go to 30% hydrogen peroxide, that is unsurprisingly 10x of what that 3% is. And this stuff is really nasty by the time you get up to that 30% hydrogen peroxide, and it's because it's so concentrated that it's going to react incredibly fast with whatever else is going on. And so, you know, I do not encourage people using anything above a 3% on a comic book, and I would really encourage you to even lower that further to 1.5% so that you're starting out with a little bit lower level on that comic book. Now that might come with a little bit slower response. It might not react as quickly or as obviously. It might take a couple more treatments. It might take a little bit more time under the light. But I think overall, it's going to be a much better result for everything because you're not starting out with such a crazy high concentration of that 30%. This is really high. And even if you have the exact same rate constant, you'll have a much faster reaction. Now, if that's all you get out of this is just an obvious discussion here, knowing that at long times, most reactions are pretty much done, and that, you know, things have shut down at this stage as things progress because we've consumed all of that hydrogen peroxide. And so it's really atypical for anything to accelerate or speed up at late times. Those are exceptionally rare situations, and it's not one that you're going to see occur very often at all. But the other thing I want to get out is this idea that the dose makes the poison. And so again, a little bit on a Friday night is probably an enjoyable life experience. You know, pounding a whole bottle Belushi style is probably a really bad idea. And so keep those things in mind. From here in the video, I'm just going to digress to a much more complicated discussion of kinetics. So if you're engaged, stick around. If you're not, feel free to tune me out at this point. Okay, so the simple one-step reaction here is probably too straightforward for anything that we're actually looking at. So to have a rate equal to the hydrogen peroxide concentration times our comic book concentration to help us get to a new comic book is probably too straightforward. This is a single step reaction here as I had it drawn before, H2O2 plus comic book going to new comic book. It's unlikely you're ever going to have a single step reaction, and in the real world what we end up with are mechanisms with multiple what we call elementary steps. Okay. And an elementary step is one part of a more complicated overall chemical reaction. And let's just take the same reaction here and break it down into a couple of elementary steps. So let's just assume that we had a hydrogen peroxide and that this busts off to give us a hydroxyl radical. And that hydroxyl radical then, we will obviously have a K here. So the rate of this is going to be equal to K times that hydrogen peroxide treatment. And this is going to be dependent on how we're going to activate it. And I'm just going to put that little triangle there. That's our symbol for delta. And delta in this case is going to be heat. And we just have a spontaneous disproportionation of the hydrogen peroxide to make the hydroxyl radical. Now, this is probably going to be the slow step for reasons that I'll describe a little bit later. But predominantly, it's going to be because that hydroxyl radical is going to have a very short half-life. And so if you go look at the Wikipedia page here for hydroxyl radical, you can see that the half-life is incredibly short. So that's 10 to the negative seconds. So that's roughly a nanosecond. So that's less than the blink of an eye by probably a lot. And so the lifetime of a hydroxyl radical is going to be incredibly short. And I'll show you a little bit more evidence here that I don't think that this is why our comic books are actually getting whitened. I don't think it's this reaction at all. Okay, so the hydroxyl radical then, at least in this simplified system, might have to react with our comic book. And then that might lead to some intermediate here where we have comic book OH. And so that might be our intermediate. And then maybe comic book OH breaks apart to give us a new comic book at the end of the day. So we have now 3 separate steps of this reaction, and we can write the independent rate laws for each of them. Oops. Let me just start that one over. Rate equals K times OH dot times comic book. And then here we're going to have a rate equal to K times comic book OH. Okay, and now each of these are going to have their own rate laws. What gets complicated about this now is if we actually want to solve all of this like in a really, really straightforward way, or really, really specific way, what you need to do is convert all of these different rate constants to a bunch of matrix algebra, go through and solve them, and then you end up in a nest full of differential equations. I'm just going to assume nobody on YouTube wants to watch me do differential equations, and we're going to ignore all the math. What you end up with instead, though, is focusing on the slow step. And the slow step then becomes what we call the rate determining step. And in chemistry, often the rate determining step is maybe 100 or 1,000 times slower than the other steps. And sometimes maybe it's even 10,000 or 1,000,000 times slower. It can be really, really slow compared to the fast steps, and the fast steps can be incredibly fast. So I'll point out here again that the hydroxyl radical's half-life is 10 to the negative 9 seconds. So that's a nanosecond. That's incredibly fast. So definitely much faster than the blink of an eye. But most chemistry doesn't happen in the blink of an eye. Most of it actually takes a lot longer, and that's because that there are other slow steps, which are the rate determining step. Sometimes this is abbreviated RDS. And the overall, what we call K-obs, which stands for observed, is going to be proportional to the primary step that's at play. So in this case, if we're going to identify activation of the hydrogen peroxide to the hydroxyl radical as the slow step, then the good news is we can abbreviate or approximate all of this as being roughly K1 in this case. We'll make all these different here, times the initial starting point. And this, by the way, is exactly why I think it's so important to be paying attention to using 1.5% peroxide instead of our 3% peroxide, and definitely not 30%. Okay, because all of the bad stuff that can happen is going to happen when you have that 30%. Now, let's just say we have two reactions here. So let's just say we have our good reaction, and that has K good, and then we have our bad reaction, and that has K bad. Okay, and so good here might be removing a little bit of yellowing from our comic book, or removing a little bit of tanning, maybe lightening a stain, and bad might be destroying the paper fiber or eating a hole in the comic book. The ratio here we then call K relative, and we want a good over K bad ratio to be high. And to get that, what we need to do is look at selectivity. And as long as the rate of K good is better than the rate of K bad, then we can prevent the bad things from happening by depleting all of the active reagent in the good reaction instead of the bad reaction. And so in addition to the rates, the changes in overall reactivity and stoichiometry is more reason why we do not want to have that really high concentrations of hydrogen peroxide. At low concentrations, most of it gets consumed doing what we want, but at high concentrations, there's going to be a lot left over to do a lot of bad things that we don't want. And so, I think that really is important to consider how much we're adding, and you're going to be much better off with a couple of very light treatments at 1.5% instead of one massive treatment at 30%. Your results are going to be better, and that's borne out in this math of kinetics. Now, one last thing I want to point out here is that the concentration here that we started with, the little bit in the brackets, and especially, when we start talking about percentages, these percentages are concentrations in the bottle of hydrogen peroxide. They're not concentrations on the surface of the comic book. So to understand the concentration and the surface of the comic book, we need to figure out how much the concentration is in the peroxide and then multiply that by how much peroxide we're adding to our comic book. So if I have a comic book like the Superman and I want to do a misting method, I might be able to add one puff of, let's say, 9% hydrogen peroxide. And if that puff was enough to fully cover the top, that might be perfect. But that's going to be really hard to do. And so I don't want that. What I want to be able to do instead is do maybe 3 puffs of 3% to be able to get a better, more even coating across the surface. Or better yet, maybe I want to do 6 really broad sweeping strokes of 1.5% to be able to get me to that same delivery. And so to be able to understand the actual chemistry on the paper, we need to know the concentrations of what we're adding, as well as how much total volume we're adding to the surface of the comic book. And so in some of my work, I will use 3%, but when I use that 3%, I add half as much as I do when I add the 1.5%. And I mostly only do that on the overlays when I want a really dry overlay. But most of the time when I'm misting, it's 1.5% because I want maybe 6 puffs, but I want really, really broad strokes to make sure I have a nice even covering over it. And so we need to know both the concentration as well as the total volume that we're adding. Oh, by the way, that also got me when I broke my original squirt bottle. I got a new squirt bottle, didn't pay attention to it. It turns out it was squirting about 3 times as much. And I measured that by squirting it onto some paper a no number of times and weighing it. And it turns out it was delivering a lot more water than I expected. And that caused some really negative results that I had to troubleshoot in the middle of the summer. So anyway, hopefully you got some value out of this. We're going to jump forward into another video. Please go ahead and leave a like, a subscribe, share with a friend. Feel free to leave questions. Chemical kinetics is definitely not something that I expect to be straightforward, and so your questions on the matter is definitely appreciated. Thanks for paying attention.